Hello, everyone, and welcome to the EEBA Online Learning Management System and our continuing education webinar. As always, I'm joined by Nancy Bakeman from snowy Minneapolis today, and we are very pleased to have Bill Warren with us today. Bill Warren's a building science engineer, is the CEO of BWES Building Science, and will be presenting on safe ventilation and airflow strategies for homes and other buildings. Maybe move to the next slide, Bill. And just some logistics. We'll have about 45 minutes today. I will be handling the questions to Bill, and please submit those in the Q&A section. And just a little background on Bill. I think many of you know him. Yeah, Mike Barsick already says he loves the beards. You know, Mike's going the other way with his beard, but Mike, I think we'll let you come on to the conversation as well, Nancy, if you can do that. But many of you know Bill from as the original project manager for the DOE Advanced Energy Research Project for crawl spaces, right, Bill?
Yep.
So we have gotten Bill out of the basement and into the main part of the house now.
I live on a slab.
Oh, how did you do the crawl space research when you were living on a slab?
I get around.
Fantastic.
Yeah, I get around.
Well, Bill is a legend, has a lot of great information, and I think that everyone is concerned about health impacts, ventilation and airflow in their homes. So Bill, we're really excited to have you today and to be learning from you.
Okie dokie. I'm trying to make sure I can make this thing work.
Yeah,
I want to do the
pointer.
I want the pointer. The pointer's up. All righty. Okay. I don't want to do any of that. Escape all of that. All right. What I want to do here, I've got a little problem technically, which we didn't go over, and I just want to have that pointer, but I don't want it to draw a line, and I can't remember how to do that. Can you walk me through that?
Oh boy, you're gonna, let's see.
Spotlight, is it? I think it's this.
Well, Spotlight is spotlighting you.
I'm sorry.
That's okay.
Okay, let's close this and just go forward because it's not. Okay. I can't get rid of this stuff down here, this line.
That's all right. Well,
it's terrible looking. How do I get rid of that?
I am open to, let's see.
It must be the eraser.
Yeah, it says go to, there you go.
There we go. Okay, I got into danger. I'm sorry, folks. I got into dangerous territory. I haven't been on a Zoom meeting as a leader in a bit. All right.
And Bill, you could just use the cursor. I think we'll be able to see if you switched back to just the normal cursor, we can at least see what you're pointing at on your screen as well.
Okay.
So you don't have to underline it and then erase it each time if you'd like.
The original cursor is this.
Mike Barsick is giving real-time chat suggestions on it.
Good, good. So you can see that cursor now, the yellow one?
Yes, that's perfect. We can see that.
Okay, very good. All right, now let's get the screen to advance. The screen does not want to advance on me.
You should just be able to right arrow click to.
Yeah, I am.
There we go.
Oh, here we go. Okay.
Perfect.
All right, folks. A little bit of technical difficulty.
No worries, Bill.
All right. I started looking at COVID ventilation in August when finally the CDC came out and said that it looks like the primary transmission has been more and more tied to airborne transmission through droplets and aerosols as opposed to contact surfaces. So all that stuff that we did about sanitizing surfaces turned out to be a lot of time in vain. And I thought the best way that I could do this was to put up some instructional videos that address this. And this is my YouTube website, so you can go there. And these videos will walk you through in a lot of ways. Like, for example, a checklist to how to set up a COVID isolation bedroom. I have a long version and a short version. This one over here is, should you, I don't recommend this, but have a large holiday gathering, how would you do that and manage your risk? So how does EEBA rate regarding COVID risk management? And it comes up to the classic building science question that we always had to answer for many years, is do homes need to breathe, or do we build it tight and ventilate it right? So we ask that question in silence because of the setup of this, but the answer is yes, we still build it tight and ventilate it right, because that gives us, the more we control the envelope, the more we know, the more we can control airflow, and we can call pressure differences. And approaching COVID risk management indoors from a building science perspective, that's exactly what we want to do. We want to be able to control the movement of COVID contaminated air so that we are able to stay upstream of that. We're able to keep people that we want to protect them. We want to keep them on the positive side, and we want to keep people that we suspect or know are infected on the negative side. So that's where that's what we're trying to do. I went and looked on the EEBA website and see that EEBA has been very active in the webinars and so forth, and putting out information on this. Most of those articles are really based on the design part of it, either through how you build or how you control. Mine is going to focus much more on strategies of what you already have. So that's going to be the distinction here, more of an operational look than a rebuild. And one of the things I notice in terms of when you look at ASHRAE material or something like that, they'll get comments down there that says, am I supposed to redesign my building on the spur of the moment to deal with this short-term crisis? Hopefully short-term crisis, is getting to be quite long, but that's what it is. So I'm going to do a brief update in terms of where we stand right now, because I try to keep my information targeted to what we know at the moment, not what we knew back in March. So it's still the standard. The change in the first end is that we, back in September, learned that masks also, CDC said, oh, we have masks actually protect the wearer. And if anybody's done any remediation work or crawl space work or anything like that, we always were wearing masks to protect ourselves, and that was obvious. It gives you a good example of how the CDC gets constrained by its institutional quality to not be able to come out and say some very obvious things. I've already mentioned that we are not going to be cleaning surfaces, because what happens for that is that we can find, investigators can find the RNA of the COVID virus on surfaces, but they can't get at the culture. So the transition is going to, yes, keep washing your hands, but cleaning surfaces is not recommended. Now, another rule here, the 6-foot rule. Most of you, I think by now, would have heard that this does not apply inside of buildings, and this is because of the building science issues of air movement. That contaminated air can move long distances, and this is particularly pertaining to the lightest ones, to what we call the aerosols. We've also learned by contact tracing that databases show that almost all transmissions are occurring indoors as opposed to outdoors, and that a small minority of people are responsible for the most infections, and those people are designated as super spreaders, and the events are called super spreader events. I'll mention a few research papers as we go through here, and this first one here, it was a study that was released, and it found that in 102 households, 53% of all household members got infected within 7 days once an infection was identified in there. And so from that, I call homes a major super spreader environment, one that is often overlooked in terms of this. But it makes sense, because when you're thinking about COVID infection, what you're looking at is how much droplets and aerosols are being produced by the person over time. And in the home, we have extended time periods. The longest time periods we stay when we're sleeping and resting at home and not out at work, and so forth. So that's an important thing to remind ourselves of. It's not just a super spreader event, is not just a large wedding or people going and celebrating inside a building without masks on. We're all aware of these things, the situation here where we are with the, right now we're at the absolute peak. We have the data going up, and this is Thanksgiving as predicted, and now we're looks like we could be leveling off again from the Christmas rush. Two factors will affect this going forward, and I'll get to those in a second. The distribution of cases is that mostly younger people are getting it, and as has been consistent from the beginning, mostly the older people like me are dying from it. That's why I'm not going to be in the room with any of you folks, because I'm worried about you. So very recently is this very good news on the vaccine, which I found to be very interesting. We've been hearing 95%, but this is being underplayed, and so in terms of the data, there's been 32,000 people that got the Moderna and Pfizer vaccines, and only one person had a serious case of COVID out of that. So that's very good news. You know, when we first started hearing about this, a infection rate of, you know, a efficacy rate of 50% was going to be considered to be good. Better news is the fact that the anti-vaxxers and stuff are less important, and the intent to get vaccine raises to 60% from where it was only 51% in September. So that's a good trend. That's going to really help how many people get vaccinated is really going to help in terms of creating herd immunity, and so that hopefully we are now at the absolute peak of this. And then the other fact that I don't have in the slides is that now we're getting inoculations, and me being over 65 in North Carolina, I'm scheduled for vaccination later this week. So us old folks are getting it a lot faster than you younger folks. This one's a lot of words on this page, but I might want to just say that this is where the documentation is coming in increasingly, that it is airborne transmission, and actually the distinction between what we call droplets and aerosols is kind of it's not a distinct, it's a spectrum. So we have very heavy droplets, and then we have very, very light aerosols, but it's a continuum in there. And actually droplets, once they get into the air, they can start breaking up and fragment and become aerosols. The lighter the particle, the farther it will fly. That's the main thing we need to know. And when we have airflow inside of buildings, it really helps it fly much farther than the 6 feet rule. Now, this, from a building science perspective, is one of the most exciting things that I think about. And that's with this study that was done in Sweden about actually going and looking at the HVAC systems and seeing how they're contributing towards the transmission of COVID. And what happened in this study is that they were able to find the virus RNA on exhaust filters, on supply registers, and so forth. But again, as with the cleaning of the surfaces, it's not viable, which means they're not able to culture it on a Petri dish. So it's fairly fragile, and down here at this red statement, this is likely due to the pathogens rapidly drying in the vents, and that's what we would think would happen because we've got a lot of airflow. So once they hit a surface like that, that's very good news, and that leads us to being able to make the recommendation that in general, and this is widely supported, as you see, the recommendation is to run your HVAC, your central systems, on continuous, because that is going to create air circulation, and that in the immediate space, like in the room that you're in right now, the fan running continuous is going to dilute whatever dose you might have within the space, which is better. And now, if it goes back to the central return or the room return, then there's greater potential for it to be actually removing the dose by making it ineffective and catching it up on the filter and so forth. So from a building science perspective, that gives us a lot more opportunity to make sure that this happens, and it's a universal recommendation is to use continuous air circulation to manage COVID-19 risk. So now we get into what I will be talking about here is to thinking about this holistically in terms of how do we manage risk and use a ventilation strategy. And the first thing is that I know a lot of intent is going into, it's all about ventilation. And there's a term that's out there that says the super spreader event happened because the building had poor ventilation or it was poorly ventilated. And that is a really oversimplification because when I started looking at it, I break it down into multiple components, which are listed on the screen here as ventilation, air circulation, directional airflow, and this also ties into pressure management. And since we do have a more knowledgeable crowd here, so we'll talk about that. And confining spaces, the smaller the room, the smaller the space, the more that the virus particles in the air will be confined, and then you have the more chance of breathing them in. And then lastly, filtration as a removal process here. But I've also included right at the top, mask wearing as a red highlighted item. And why is that? Well, that is our primary defense. And when I have watched, my evidence for the fact that we are not wearing masks in homes has to do with a lot of Zoom meetings that I've participated in, and nobody's wearing masks in their house. And I think that's the natural thing to do. And I've gone and looked at CDC literature and so forth, and it's not specifically being stated. And but when it comes to having individuals that are not wearing masks that are either have been identified by contact tracing or have been tested positive or are showing some symptoms, those people really should be wearing masks. So very important to do that. Now, the ventilation strategies that I cover, you've got them in detail, particularly for the home, when you go to that YouTube website, and then you can look at them there. So I'm not going to go down on so much over those particulars that are on there, but encourage you to go to that place.
And Bill, just to let everybody know, I did post the link to your YouTube site
Great.
In the chat section, so people have that.
Great. Yep. Now, here's what distinguishes the EEBA home, is that it is not, I'm trying to move something on my screen here, but it's not moving around to it. I'd like to get this down because you're seeing this too, aren't you? You're seeing this toolbar that won't go down any further.
No, we don't see the toolbar, Bill.
Excellent. Okay, great, because I'm seeing it and you don't. Good.
Okay.
So the typical home, it's few and far between that you have anything but exhaust ventilation. And EEBA homes are going to be high performance homes. So they're going to have some types or multiple types or a single type of fresh air or outdoor air ventilation, as we call it in commercial buildings. And so this is an advantage because whenever we can mechanically have fan-driven ventilation systems, and just to be sure, ventilation means the moving of air from inside the building to the outside, which is exhaust ventilation, or moving outdoor air into the building, which we call outdoor, and some folks call it fresh air ventilation. But both are fan-driven forces. So in the types of things that we expect to see in EEBA standard homes would be neutral systems, which would be energy recovery ventilators and heat recovery ventilators. On the positive side, we would have the simple system, which is very good for COVID, which would just be outdoor air makeup to the central HVAC system. And then in my neck of the woods, where we have hot and humid climate, the whole house dehumidifier with outdoor air.
And
those
just for the audience, Bill, you're in Raleigh-Durham, North Carolina.
That is correct. Actually, I'm not in Raleigh. I'm in Chapel Hill, man.
Oh, way better.
No, doesn't matter. I'm in RTP.
Nice.
And the bottom category, negative exhaust, that's what we have, but it is a functional tool for sure, particularly bathroom exhaust, that can be on the positive side. The other fans, we have to be wary of them under certain situations, and those would be the range hood and the laundry dryer, because of the fact that they're going to create a lot of airflow going towards those units, and we're going to be trying to stay upstream of anybody that we think has got COVID-19.
And Bill, in your analogy there, the downstream would be where the exhaust is exiting the house. So
Yes.
things would be attracted to that area of the house. Staying upstream, you're on the other side of a potential person from that.
Yes, that's your basic, and this is universal behavior, not just to your home, but particularly when you're out in other buildings. You're trying to, your job now is to keep yourself as safe as possible. Beyond wearing the mask is to look around and see where the supply registers are, see where the returns are. And you want to stay away from returns and away from exhaust fans, because that's going to put you downstream of a potential contaminated COVID airflow.
Mm-hmm.
My screen is locked up again. I don't know why.
Try the right arrow. There you go. We got it.
There we go. Okay. So fortunately, finally, the CDC, as of January 7th, has finally started to do a few things that are good here. And but it's fairly interesting. They're still very big on opening windows. And you notice how they've addressed this in the middle of winter. They've got everybody dressed up inside with like they're outside. And this is, if you can do this, you're great. But it's the colder the climate, the harder it is to do this. So this graphic just cracks me up. And my method is to do something completely different from this, is to use very controlled amounts of airflow to move the least amount of air. And particularly when we get into, say, a COVID isolation bedroom, is to move enough air out of there that we just create, with the door closed, a depressurized condition. So any COVID contaminated air stays in that room and then is exhausted directly to the outside with with what we see right here in the graphic. If you can see that, is a little double fan stuck right in the window. That's the first time I've seen the CDC actually showed anything like this. But look at their language. It says, consider using a window exhaust fan. Be sure to say, no, and if we are trying to do isolation, then we are going to use something to exhaust that room directly. So fortunately, they're finally coming around to this point. It's taken a while to get them there, but let's go forward. Oh, the other part about this is the first time I've seen the CDC actually show these folks are all wearing their mask indoors. And probably the most important place we can wear the mask is indoors, because as I've shown you, indoors is the biggest super spreader event. And that's where you need to do them, particularly if you know that. Oh, there's the, I did that, had that coming in there. I'm going to talk a little bit now on the open window strategy. This is the widely recognized strategy that is done by CDC, it's done by EPA, and it's done by ASHRAE with various amounts. And the deeper you get into it, ASHRAE gets more wordy about it, but nonetheless it is. So if you know from the basic of building science, is that if opening a window is a passive ventilation system, it is the primary way that residences are provided with ventilation air in the code. Code provisions say in a building you have to have an operable window. In a room you have to have an operable window. That's what it is. If we know from our principles, when we get airflow in and out of buildings, they're created by three forces: wind blowing on one side of the building, and negative pressure on the lee side of it, stack effect, warm air rising in the wintertime, reverse stack effect, cold air sinking down through the structure in the summertime, and by mechanical effect through fans. So all of the CD's recommendations about open windows, to me, only really apply when you don't have any COVID infectious conditions in the house. That's fine in that situation. That would be just prophylactic and a decent strategy. But as soon as we get to having either a person that has been identified by contact tracing or has been tested positive or has symptoms, then we do not want to do this, have open windows as a passive ventilation strategy. And I'll show you why. Let's make sure we understand these basic building science rules. When we're looking at a conditioned space where we're heating and cooling it, we're isolating that space from the outdoors by creating an envelope. And airflow going in and out of that is going to be determined by these rules. And if you exhaust the cubic foot of air out the building, that means someplace else the building will be bringing it in through air leakage or through a designed hole in the space. If that does not happen, if we are just exhausting and we don't have, if we're looking at something like, say, a passive house, which is built to very tight, airtight standards, if we run an exhaust fan, we may not get very much flow there. What we'll actually start doing is creating pressure differences in that. But for the most case, we're going to be looking at this 1-to-1 ratio. So 1 CFM goes out, 1 CFM comes in. 1 CFM comes in, 1 CFM goes out. And tied into that is this rule here, is that ventilation airflow is going to take the path of least resistance. So when we open windows in a cold scenario, like we showed in that CDC graphic, that's going to create the path of least resistance. So if you run an exhaust fan, this air is going to largely come in through that open window because that's the easiest place that it can come in. And that's what causes me concern, is airflow coming in from outdoors into a room where we have COVID contaminated air and then transporting that COVID contaminated air to the main body of the house. So anytime more air comes in than goes out of that room, COVID contaminated air will move to the main body of the house. I hope we all understand that, because that's a core principle of operational control for COVID risk management. So these are building science typical graphics we're seeing. The first one is showing wind effect. The second is stack effect and combustion and ventilation systems. The concern that I'm looking at here when I think about COVID is being downstream and upstream, and these arrows that come in these cases here, and these here and here, are arrows that are showing airflow directions that could be transporting COVID infectious air into the main body of the house from a bedroom or from a spot where someone that is a super spreader is sitting there reading a book and coughing or whatever. So that's what we're trying to work against once we know we have suspected or identified case of COVID. So let's go through a few of these schematically. So in this situation, we have a bedroom where we've got a person that has got COVID. So they're producing some contaminated air in that room. And we put the wind on the building. The wind is blowing towards that window, and we're using the open window effect because the CDC told us to do that. And so air comes in and it starts mixing, and this is what ends up happening. So all of the contaminated air in this bedroom under these conditions, very variable they may be, and at different velocities depending on how fast the wind is blowing, are going to be moving from that contaminated bedroom out into the main body of the house. And the critical area is right here at the doorway. That's where the exposure would be most intense, particularly say if the bedroom door was closed and then you open the door to go speak to someone who's in the bedroom to see how they're doing, check on them. In that situation, there would be a gush of that contaminated air that's in that bedroom, all coming by you at an accelerated velocity. And so this is my confining space, which I'll show you again a little bit. That's very problematic. We don't want to be in confining spaces when we have directional airflow bringing COVID contaminated air. All right, so let's look at another example where we want to do open windows. So we're going to put, we've got another person in the house that is got health issues or they're elderly. And as we saw from the graphic, the most people that are having the worst cases of COVID are the elderly and health impaired people, and that's the most deaths as well. So if we use this, and one of the clear things that's now stated in CDC and EPA and ASHA is have cross ventilation. Now, on a single story building, that means we don't have any way to make that move up into the second floor. So we would have this condition. So let's look at what happens now when we have airflow coming in. This is what we get. This is the worst situation you could imagine. Now, her circumstance, if we put it in bedroom number 1, not bad. But if we elected that we think that maybe we want to ventilate that bedroom of the elderly person, and this cross ventilation would be good, this is what we get whenever the wind is coming in. The green arrows show into the contaminated bedroom, and path of least resistance in right here, path of least resistance out right there. So that would mean that this is a fairly good representation of what's going to be happening. Now, this air is getting diluted as it comes in, but nonetheless, these particles of COVID-19 are not being removed yet. They're not removed until they get to here. They've got to get out before they're actually being removed. These particles are just moving along. We're not getting any dilution effect of ventilation in this situation. And that's important to think about. So this would be the worst case situation. So that's why I'm a very antagonistic position once we get to COVID contamination to have passive open window strategies. We'll look at one more case here, which would be exhaust fan effect. So we're going to turn on the dryer. We turn on the dryer. A typical residential dryer is going to pull about 200 cubic feet of air per minute out through the dryer so that it can remove the water vapor that's the water that's being evaporated, and it's in the clothing and out that. So what happens this? Now we've got our open window, 1 CFM in, 1 CFM out, 1 CFM in. Air is going to take the path of least resistance. This is a pretty good representation of what we're going to be seeing, is that most of this air to supply the dryer, where's it going to be coming from? It's going to be coming from this window, and we have somebody that's got COVID in that bedroom. And so this is what we get. So let's think about this in terms of the 6-foot rule. So this exposure area is the worst to me because it's that confining space. So it's going to be a 3-foot, 8-foot corridor. We're going to get the most amount of air, but nonetheless, all the way over here, this is an accurate representation of the fact that the mother and child are at elevated risk because of this airflow pathway, and this would be very well established. We could see this. Now, I don't know whether you've ever done smoke inside a large space. The airflow is very, very dynamic and disorganized, but nonetheless, the overall conditions is that whatever's coming here, eventually, while this dryer is running, it's all going to go out that dryer vent. So I could be more representative and make these clouds a lot bigger, which is what they would be, but I'm trying to demonstrate the principle here as opposed to being fully faithful to the to what's happening in these dynamics. So here's where I actually identify this confining space, which is something that when I started looking at this, I don't find this to be something that is being addressed very well by others. And in my particular instance, I've said it already, the worst confining space we would have would be right at that door. We're going into a COVID isolation bedroom. So where did this strategy come from? I think this is a very interesting history lesson to see how institutionalized things happen. There's a lot of things in our building code that have been there forever, and that's just how we do it. It's remarkable how many things are in the code that way. So historically, it came from about 125 years ago when the tuberculosis cases were increasing a lot. And tuberculosis is an airborne transmission, and it's very, very easy to transmit it. So they began using open window strategies, and this is one where the actual system is to put this bed is on a roller, and you can get it in and out. So you can close the window at night, but you're basically getting the person outdoors, and you're bundling them all up. And that's what you would have to do with these open window strategies to make these things work. But remember now, if the wind is coming, now back in this time, they weren't having fans in this building before fans, but they did have stack effect, and they did. So right now, if this person is producing tuberculosis virus, all that airflow is going to be going back to the rest of the body of the house. So sometimes it worked and sometimes it didn't, but at the time, that was the best you had. This is an isolation. This is during the Spanish flu. This is an army barracks, an army, whatever it is. And they're using the open window strategy here. Very minor, given how this room is just packed full of people. And this is clearly a super spreader event, which is what very much the Spanish flu was. The Spanish flu was certainly a pandemic major in terms of how fast it spread. And maybe it estimates that 30 to 60 million people were killed worldwide from it. So it's not enough to do this. Now, I did say, when I've looked closely at this photo, so these open windows are not helping us enough. We have just too many people in here. But look at this here. This fellow in the green circle is wearing a mask. And these two, I can see that they have masks on, but they've taken them off. And this supports my opinion that particularly when you get in the home and you get somebody that's sick, the chances of them wearing a mask rigorously goes down. And that's the worst thing that they can do. So that's why we really need to go well beyond the mask if we're dealing with COVID contaminated air, and we have to go to direct exhaust. So my recommended strategy to do isolation is, once we have been contact traced individual, we have someone tested positive or has symptoms or combination, we stop the open window strategy. The open window strategy is fine if we are confident that we don't have anything. It doesn't hurt anything to have open windows. But what we switch to instead is we go to a direct exhaust ventilation strategy with a window fan temporarily installed, or with an attached bath and an exhaust fan in that bathroom. Those are the only two methods that meet the standard. So if we go back to our graphic here, we say, yes, we're going to do this. We're going to put this fan in. We're not going to do this thing of another option is to place a fan as close to the window. No, we really want it right in the window, and I'll show you the reasons for doing that in a second. So what we're going to do is we're going to start thinking of ourselves as hospital industrial hygienicists. So this is a booklet put out by the state of Minnesota hospital, and it was their plan to address the fact that they were going to overrun their ICU units, and they wanted to have rooms to put people with COVID in them where they could do depressurization control in those rooms. And so they did this in this method right here, which is they went to a window, popped it out, put a piece of plywood in it, cut a round hole in it, ran a flex duct to it, hooked up a scrubber, a HEPA filtered air mover, and ducted it directly to the outside. So this represents a and their terminology for this is airborne infectious disease management methods for temporary negative pressure isolation. So this is exactly what we'll do in the house with the constraints that we have in the house, as opposed to having professional mechanical engineers and industrial hygienists to send it up. We can replicate that and come very close to doing that and deal with the limitations that we will have in the house. So, so this is our bedroom, and what we're trying to do is keep the people that are not inside this room protected by making all airflow go this way and be forced out of the building and out of the hospital in this case here. Next thing it says, you're going to use a HEPA fan with a good filter on it. Now in residences, hospitals generally are required to put filtration on exhaust. So we don't have that issue. So I'm fine with just using a window fan or using a bath fan without this. And I tie this into the fact that we have very, very few exposures in the outdoor environment based on the data. So once we discharge it to the outdoors, the strength of the COVID contamination is diluted enough that it is not going to cause a problem by exposure to somebody outdoors. I guess except if someone was sticking their head right in the exhaust. But even under those conditions, I don't think that that's a likely scenario here. So I say the filter can be optional in the homes, but you can certainly do this. It's a strategy, and I cover that in my videos as well to do that. Their point is they want the returns covered. And they want the returns covered in here because they don't want this contaminated air going back to the central systems. Now, remember that study that was done in that hospital in Sweden said, we found the RNA of COVID, but it did not culture. So I can go along with this. I recommend if in isolation bedrooms that the supplies are taped off. But what I want to do is I also want, I also want to tape off these returns in the bedrooms when we have this condition. And my video, I have a video that's called just that, how to tape off supply and return registers in a COVID isolation bedroom. And here's where you see one of my a screenshot from one of my videos where I go through the checklist of how you actually install one of these fans. And if you've looked at any of this, there's been large experiments by municipalities with schools where they've attempted to ventilate classrooms by putting box fans in windows in the classroom. And they put one fan blowing in and one fan blowing out. And guess what they learned from that? Everybody was freezing. the cold of the climate. It's just, so it's a great system. And it brings you back to that graphic that we were looking at before. If you're going to do that, everybody's got to be bundled up, and you not only have to be bundled up for the temperature, but you have to be bundled up in addition for the wind chill effect by these fans moving air in and out of the building. So that does not work. But what can work in a situation is here, and in this group, particularly folks that have digital manometers that understand pressure differences, that know how to set the pressure across the door for no more than 3 pascals, those types of things. You're very well versed in being able to do this. What we're going to try to do is move a little amount of air, and you can see that here. In that, this is a 2-fan setup. Each fan has got 3 speeds on it. I've taped one fan off completely because this is my bedroom. I know that I'm getting pressure difference across my bedroom door when it's closed. And when I crack it open, I know that my airflow is going from the hallway into the bedroom. So I'm very comfortable that this works. And you can do a worst case scenario if you wanted to. You could go in and check. This would be your combustion safety pressure text that you would do is, well, what happens if I run the dryer? What happens if I run the range hood fan? So you could adjust for all those things. I don't think that that's prudent to do for those big CFM temporary airflow loads, because we can open a window to offset that when we're doing that. And that's exactly what I recommend that you do that. What we want to do is just look at it in terms of what are normal conditions and make sure that we get this airflow going out. And the more we can keep that bedroom door closed, the better we can keep this condition, that bedroom depressurized and dominantly exhaust that air directly to the outside where it can't do us any harm. That's the contaminated air. And by doing that, then we can make the whole building much more comfortable, and we don't have to have people walking around with, down parkers and knit hats on. So that's the basic core of this strategy. And as you can see, I go in and show you, like, I've taped off the joint between the bottom sash and the upper sash. I've also, just to explain, there's some black poly that's on the window. I had to do that because the sun was so bright I couldn't make the video camera work on it. Tape off the fan, make it nice and tight. And just to cover that, just briefly, I'm doing all of this so that when this fan is pulling out, it does not start to pull air back in around these cracks. And the purpose for that is so that I have better control, and also so that I have less cold air coming directly into this room. And that was a big point of mine, to make sure that I minimize any comfort problems we're going to have when we do this type of ventilation. So this is a schematic look of this condition here. Here's our bedroom. We've run a fan in it. We've got the window opened in. We're confining this contaminated air so that it's not going into this confined space of this doorway and down this hallway. And this is exactly what we want to do. So this is infectious disease control, temporary infectious disease control in a COVID isolation bedroom. So we're reading the same standard, performance standard, as that hospital bulletin from Minnesota is pointing out. This is what we would get. And by keeping the speed of that fan set as low as possible, then we can offset this outdoor air that's going to be coming in the building and make these other rooms less comfortable. Our immediate thing, the colder the climate, to address whatever we need to do in terms of setting this airflow down, we can offset that directly by going to the thermostat and pushing it up a degree or two. That's the first thing that we can do. But say you had someone in, say, in another bedroom that was getting cold, we could do more work in that room there with a temporary space heater in the contamination bedroom, so forth. So it's much more doable than CDC and ASHRAE make it out like you can do this so long as nobody gets cold. No, if you use a control strategy, and you can check pressure, you can check it with a smoke bottle. Obviously, if you've got a digital manometer, you can certainly check it with that because you can get read down to a Pascal a difference. And we can get in the range of 2 to 3 pascals across the door. We're great. But you can also check it with the back of your hand, and I show you how to do that in my videos. How are we doing for time? I'm not looking at that. What do we have left, Aaron?
I think we've got 13 minutes left.
Oh, great. Great. Okay.
Hey, can I just ask a quick question?
Yes, please.
If you're looking at this house, would it be better to put the infected person in the master bedroom where there is a bath fan attached to the bathroom that is part of the master and get, I'm probably throwing you a softball, right, Bill?
Yes, exactly. And that's a very good strategy. I cover that again as well. And it's a particularly good strategy for, because we'll cover this at the end, but I'll mention it now since you've asked that. Yes, you've already got the built-in exhaust. So what you have to do in that situation, I cover this in the videos, is you're going to make sure that the fan's working, right? So we can check the pressure at the door. If we establish we've got airflow, you can use tissue paper up there. If you've got a digital, you can check it that way. But then you've got everything's installed, and likely you know that this is going to work because if you can run your bathroom exhaust fan continuously, that and particularly an EEBA level house, you're not going to make people very cold in other locations, particularly if you've got outdoor air ventilation on the house. So excellent question. Yes, that you can use either a window exhaust fan or a attached bath fan to do this.
Hey, just maybe a question on this from our audience. What happens if you have an HERV, if there is a supply in the bedroom and an exhaust in the bathroom? Wouldn't that distribute the virus around the house?
Well, the the supply is in the bedroom. Yeah, we don't want to. We're trying to get this confined. And when in the COVID infectious bedroom, my recommendation is to tape off the supplies and returns.
Okay.
That's the safest thing. For sure, the returns. The supplies, I'm less concerned, particularly if the return is in the bedroom. I'm less concerned about that based on that Swedish study, and also the fact that all this work to try to see if you can get the good news for us is this virus seems to be very fragile. It does not, it's not robust. So once it hits the surface, it dries out. And I feel like as it transmits itself through the duct system, and based on not just feel, but based on that study, non-viable. So that's my answer to that.
Okay, thank you.
You can also do this now. Another thing that ASHRAE says that, well, don't do this unless, if you've got people with asthma or something. Well, you can use the method here of just using the box fan, and you can go, this must be 20 or 30 videos plus mine. You can just look at mine actually, and just take a box fan, 20-inch box fan, put a HEPA 13 filter on the outside of it, blow the air in. The only problem here is that we've got a lot more air coming in, and likely that's not going to work in really cold climates to do that. But it's another good system. And now we really know where the airflow is going. We've got it coming in here. We'd want this and your sizing here, you would want, and now if you use the same fans and you put a HEPA filter here, you know that you're going to get less airflow out of this because of the resistance of that heavy duty filter than you are here. So we're going to know this one's going to pull more air out and that one's going to be able to push in. So we'll get what we need to do in that scenario. All these are covered in the YouTube videos. This is something I just started in the last hour or so, is just to kind of come up with and I really want you to think about this as you're just looking at this as a holistic strategy that has multiple components and then different subcomponents and so forth, so that you have a complete strategy as opposed to just saying, I have an ERV, I'm fine. That's not, or I'm just going to run my fan on continuous, or, I assume that the person that's got COVID is wearing their mask all the time. So it's a real rough spreadsheet at this period of time here, but I'm just going through that, and I'm not going to spend any really time to go through this, but I just want you to think of it as a decision process. Every house that you're looking at is got a number of decisions to make. They've got, continuous operation conditions to look at, and then you have isolated ones to deal with things like your dryer fan and your range hood fan. First of all, like on the dryer fan and that, you can really solve a lot of that by just opening a window. Possibly you might open several windows to offset it. But the folks here that are familiar with being able to do pressure control will be very comfortable with being able to do something that minimizes risk. One thing about this is that in the next column here, we've got the component, subcomponent, no COVID-19. Well, you're really quite easy with that. You really don't have to change much, particularly if everybody's isolating. But as you get to this other condition, then you do far more, and you're far more rigorous depending on things. Like a key variable here would be is that you have a COVID infectious person, and Uncle Bob, wear your mask, please put your mask on, and he's not doing it. So then you become more and more rigorous as you go through it. So here's some particular cases that I envision taking place. So we're going to talk about it in terms of airflow and pressure management to get it into a little bit more technical side of this, and give you just the general things that you need. Like that's how I always used to think of it when I was doing lots of air leakage testing, is to think, do I want to be positive or negative here? So when you get into a situation like my household where we're both able to stay at home all the time, everyone is isolating, you don't really have to change your behaviors whatsoever. It's fine to run your air handler continuously. It will result in a higher utility cost. Certainly if you have an ERV or fresh air vents installed, you would normally use them anyway, so there's really no change in that, whatever you're doing, but you don't have to be really concerned about this. The case that you might be, when you would become concerned is that the dishwasher goes on the blitz, which I don't have as a category here, but so then you would consider temporary measures. Let's say you had to have somebody come in and repair the dishwasher, and you see that they're not wearing their mask very well. You don't know that person. So your first thing is to suspect that anybody that comes into your home that you don't know their behavior patterns, that you suspect that they could be contaminated. And so you treat them. So that's when we get into this whole notion of staying upwind from somebody. So if they're working on the let's take, for example, you've got like in our house that we're showing before, the kitchen is at the end of the house. So what we could do there is temporarily, we could run the range fan while they're there, and then just stay away from that so that the air in the kitchen is going to move towards the range hood, and any contaminated air that person might be putting out because they're not wearing their mask too good would be going in that direction. So that's a simplified way to start thinking about it, but you can apply this to every condition now that you have the core principles down. A very common situation, and this is probably the biggest cause of super spreader events in homes. Not everybody is isolating in the house. Somebody's got to go to work. Our economy continues to run. That means an awful lot of people are in close contact, and the higher the density of people in the house, the simpler the house, the smaller the house, the more likely this is problematic. So what we want to do in that situation is take that house member and treat them in a negative room, keep them negative. And this would be the great example of, let's put them in the bedroom with an attached bath and run that bath fan continuously, verifying that the bath exhaust fan actually works. And that would give us a great deal more control over that scenario there. And a good one example of this is my doctor and his wife are both having to go out and work every day, and they have got kids at home. So we talked about it, and I said, well, let's do this. And he said, that sounds like a great idea. So they don't want to, you know, they're in high, particularly the doctor, and she's a school teacher, but she's at less risk, but he's a doc. So, and he doesn't work in a hospital. He works in an outpatient office. So a perfect choice in that scenario there. Now, the next one here is if we have someone that's at risk, and think back to when we went over that, cross ventilation system where we're opening a room in a confected room and opening a room in the elderly health risk person's room, and we're getting all the airflow going there whenever the wind's blowing in the right direction. So that situation, we want to stay positive. So here's the first thing we can do is if we have a fan-driven HVAC system, we've got supply in that room. We verify at the door that we've got positive airflow over that. With the door closed condition, we've got pressure difference across it. The standard thing you would do in, say, an Energy Star rating or any type of high performance, and that in those cases, we're trying to get that pressure down. In this case, we like to see that pressure. It's totally different, but that's what we want to see, some pressure difference on that. And so we're going to keep them at that state. Now, one thing that would affect this would be, I think in particular, would be if you're in the part of the country or whatever where you have returns in the individual bedroom. So this one would be even easier because we could block off the return in that bedroom that we're trying to keep positive, and then we're certainly going to be able to maintain pressure as long as our duct system is working and we don't have excessive duct leakage or anything like that. So that gives us a really good start on that. Now, to say we're not quite there, another simple thing we could do is we could actually create less resistance to airflow in that duct. So we could go up into the attic and we could check the flex duct or whatever, make sure the airflow is good, make sure the damper's fully opened, actually take off the ceiling register or the wall or floor register and increase that airflow as much as possible. And that would give us, while that person is in that bedroom, the most possible protection by keeping them positive with respect to the rest of the house and any other people that are not self-isolating in that house. Not a perfect solution, but while we have them in the bedroom, it's the best that we can do, and far better than I think that most of our nursing homes are doing because of the way infections are spreading in those. Now we have contact tracing, exposure. So we haven't been positively tested. These days, once you've done that, it's getting very easy to get tested. So this is going to be much less of an issue. We want that condition to be negative, and the same is once we get into that. And the difference between the two is if we've got somebody tested positive or has symptoms, then we get much more rigorous in terms of, following all those items that I've gone through. And that will give you a full strategy for addressing this. Everything from we don't have to do anything to intermediate steps to the whole basket of changes. I think I got the slide. Did I slow it? Yeah, I think I did that. Yeah, that's a mistake. I shouldn't have it there. So that's the end of this presentation. I think we're in good time. Do we have questions that you want to go through? And I could add a little bit more on if you don't have that.
Yeah, one question we had, and I think I have the answer for it too, but do you see adding higher MERV level filters as an overall strategy?
Well, this gets into the standard advice, and MERV 13 is what we can get into central systems. Higher than that, it gets pretty hard to even do that. So you have to have a specialized unit to be able to deal with that. That's well above what we need to contain viruses. So I'm very comfortable with that being the choice. I didn't talk about room air cleaners, which is important here. You can't, that's easy. And they've gotten so cheap on Amazon, you can get one for 50 or 60 bucks. If you want to have one that's even cheaper and you've got a 20-inch box fan, get a MERV 13 filter, tape it on it. My videos cover that. That's a great filter, great room air cleaner. The case here would be is that if you get into where you're trying to do this, then you're going to start adding them more. So you would use more of them. Main body of the house, living room. The more presence, the more people are working outside of the house, so forth, the more you'd want to use those.
Yeah. Bill, one other area we hear a lot about humidity control, and that
yes.
you what's your advice on humidity?
Well, humidity control is much more complicated. And I have not put a lot of time into addressing that now, other than the main key is to keep our airflows low. That's what would be the thing. Then after that, in an EEBA home, you're much better positioned because likely you're going to have variable speed airflow and you're going to have multiple stage compressors. So you're much better suited to be able to doing that. But to make sure you do that, and then it's going to come down to a thing of monitoring. And I am very strong on getting people to learn about dew point, because relative humidity it's a relative term. It doesn't tell us anything. But if you think in terms of dew point, then you can actually know quantitatively how wet my air is. And we're trying to keep that number at 60-degree dew point and below. And we take additional steps. So in the case of somebody that it doesn't have anything else, a standard system, that means dehumidification, temporary dehumidification. Going forward, I mean, EEBA homes, I think we're going to have we've got much better envelope air control and so forth. So I'm less concerned about that than I would be in an older home where we're going to try to do some airflow in it. And if this is still bad in the summer, I'll do some videos that will really address that. It's the biggest, it will be the biggest challenge, as you're smiling and no. Yes.
Right, absolutely. Bill, if people are going to go upgrade, I think there's some actionable things that we can each do right now based on your advice. But if people are going to go upgrade to a MERV 13 or MERV 16 filter today, what steps do they need to take on their central conditioning unit to make sure that they don't have too much pressure drop or, create unknown problems?
Yes. Well, in the wintertime, we have less issue for that. I have certainly had problem houses where they've gone into doing a filtrate type filter on the return with a lot of duct leakage beyond it. And the house has just gone crazy because the ductwork was located in a crawl space, say, and then the humidity loads and then they drop the thermostat down so they get the sensible temperature down to whatever they want, 72. But then we're getting dew points way too high, above 70 degrees. And that gets to be way too much.
Mm-hmm.
That's my primary issue with that. On the conditioning side for heating, it's less of a concern, but if you're getting into doing that in the central system, then it's good to have a professional come in and take a look at the ductwork and verify everything it can handle that. Beyond the qualitative thing of I just put in that filter and I'm not getting enough conditioning out of it.
Right. Great.
The other item on that was, you get too much of a filter resistance in the air conditioning system, and you can start icing up the coil as well. So it's far more hard to do this in the summer, in the hot and humid summertime, than it is in the wintertime.
Great. Mike Barsick, do you want to come on? Do you have any questions or comments, thoughts?
I really just wanted to say I thank you, Bill, and thank you, Aaron. Not anything really new, just to kind of reiterate some great points. Bill, I was going to ask, can you go back to that slide that showed your pressure scenario? I thought that was really helpful, that just sort of summarized. And in my feeble brain, I always kind of go back to that.
Which one is it, Mike?
The second to last slide that just talked about airflow pressure management. I think that was it, right? Number 48.
48. Yep.
Yeah.
I just thought that was great because, again, the simple thing is, pollutant needs pathway to the people, and it's pushed by positive pressure, and blah blah blah. But the nice alliteration. But the idea that if to simplify it down even further. Oh, sure. Start my video.
I want to see you, Mike.
I look kind of like a thug today. I'm wearing my thug hat, but no.
Are you keeping your windows open, Mike?
Yeah, I'm urban camping in Minneapolis. Yeah,
get the down jacket on, man.
Yeah. No, I'm. Stop making fun of my appearance. All right, I can't help it. No, what I was going to say is, I think that just keep that perspective in mind, that the person that we're trying to keep away from us, they're at the lowest pressure. And so we want to do what we can to put them at the lowest pressure. And a small continuous operating exhaust fan is a great strategy, and lots of ways to do that. And why isn't that a huge fan? Because of comfort. And so, you know, we want to, in essence, isolate that chamber. I definitely clear off the return. I would probably make the case for closing off the supply and just let all the air flow into that room from the rest of the house. You're right, it kind of depends on the scenario, but and maybe give them a space heater because we're in the winter time now. But if that room is at the lowest pressure and all the rest of the air that gets into that comes from the main part of the house, that seems to me a safe thing. And then the alternatives, what you mentioned again, was you've got a person that's at risk. We want them at the highest pressure. And again, it'd be great if we could just blow air on them from the outdoors, but that's probably going to affect their comfort too. So I think, Bill, you did a great job explaining. I just appreciate the chance to reiterate.
Just to add to that, Mike, I mean, I love the analogy. This is exactly how hospitals think about it.
Yes.
Right.
Absolutely.
And so we're taking that same engineering approach and applying it to our own homes. I love the idea of, you know, if somebody comes into your house, you know, how do you think about it? It's a really, really great education for everyone, Bill. And I thank you for that.
It's real world.
Definitely.
Maybe we should do a poll. Who had a major appliance fail in the year 2020 that involved, you know, having, I had several, but I fixed it myself, but most people are going to have someone come in and do it. So yes, we want to be safe. Yeah.
Right. Or even just, you know, we had, you know, you might have people over, you're getting together outside, somebody has to use the bathroom. Okay, great. Now, how do I create?
I pointed to the tree. There's the tree back here.
All right. So I'm going to test you two. So that's exactly the situation. You're outdoor and you have somebody come in and I got to use the bathroom. What is your control strategy?
Bath fan in the bathroom.
Turn it on.
Crank
Turn
it
it
up.
on. But just you're going to have company over. Everybody's going to be having some cocktails, and you know, some people say they need to use the bathroom. So just run that bathroom fan the continuously by there. That is definitely a confining space. If we're not running that fan, the next person that goes in and there's no fan running, that contaminated air is there.
Right.
Well, I mean, with my wife has absolute control over this, so the answer is nobody comes in the house. So that's another strategy.
Yeah,
it is extreme. And that I think again, it's all about the positive pressure and the negative pressure and where we want, and you know, but absolutely good, you know, good scenario. I think your videos are great too, Bill, because I think showing people what you mean as opposed to saying, well, just attach a filter to the box fan and put it on your unit. It's like, well, yeah, there's sort of right ways and wrong ways to do that. So I want to make a push for, if you're listening, go watch some of the videos, because I think especially for non-technical people, I've tried to send non-technical people to your to your YouTube channel to watch this stuff so they can kind of grasp this is what we mean. So
no, I think it's great. Well, I just want to, Mike, I want to thank you for the guest appearance. You're always a welcome guest at EEBA. And Bill, I want to thank you for the incredible education session. I just want to give a plug that EEBA.org, I think we've got almost 100 hours of building science education up at that site now. So lots of great stuff on healthy indoor air quality strategies. And Bill, I think we'll try to create a link on the EEBA YouTube page to your YouTube videos to help out the community.
That's good. And of course, people that are watching, if you find this information useful, share it with others. The standard YouTube thing is to click the like or the subscribe thing. But if you're active on Twitter or anything like that, I don't know anything, I'm not do those things, but if you would retweet or whatever you do, that would all be well appreciated, because and take this information, steal it, redo it, make it better. It's just, you know, it's, you know, what my goal here is I sign off every time I'm saying stay safe and stay sane. And the more we can use science and facts and engineering principles and physics to come to the place where we don't have to be worried all the time, the better off we'll be.
I love it. It's great advice, Bill.
Love it.
All right. Thanks so much, everyone. Stay safe and healthy.
Stay safe, stay sane.
Good job, guys.